So here we're going to look at an example of using Laplace transforms to solve a differential equation. So we're going to return back to our example of the thermal mixing tank. And in this example of the thermal mixing tank, we are going to have the feed 1 temperature, T1, change at time t equals 0. And so this would be a linear differential equation. And what we want to do is we want to be able to solve this differential equation to get how the outlet temperature, T, changes with respect to time. So initially, the thermal mixer is operating at steady state. And then at time t equals 0, the inlet temperature makes a step change from 25 degrees C to 30 degrees C. So initially, we have 25 degrees C, and it moves to 30. Feed 2 stays at 75 degrees C, and the product temperature initially equals 50 degrees C because it's a mixture between the two. The flow rate feed 1 is 5 kilograms per second, and the flow rate feed 2 is also 5 kilograms per second. Now, according to assumptions that we can make about this problem, the fact that the mass stays constant with respect to time, we can derive the energy balance as shown here. We can also put this equation into deviation variable format as shown here. And so now what we have is we have a first order linear non-homogeneous ordinary differential equation. As we can see, according to the energy balance being put into this particular format, we have a time constant tau being equal to mass over F1 plus F2. You can think of that as sort of as the residence time. And we also have the process gain Kp, which is equal to F1 divided by F1 plus F2. Now remember, the process gain is how much your outlet variable is going to change with a unit change of your inlet variable, or sorry, of your input variable. Okay, so recognizing these substitutions or groupings of constants, then our differential equation is d temperature hat d time is equal to 1 over tau times Kp times T1 hat minus T hat. And we have an initial condition of T hat equal to 0. Now the reason why the initial condition of T hat equals to 0 is because the initial condition for T is equal to T naught, or I guess typically we write it as T bar. So let me go ahead and do that. Okay, and T hat is defined as T minus T bar. So therefore, our initial condition for T hat is 0. This is one of the advantages of using deviation variables, is that we start with an initial condition of 0. That way, when we do a Laplace transform, the Laplace transform of our time derivative, we don't have a initial condition term cropping up. Okay, so first of all, T1 hat looks like the following. So at time t equals 0, so initially T1 hat is equal to 0. And then at time t equals 0, it makes a step change up to 5 degrees C. And just for simplicity's sake, we're going to call that just the magnitude of that step change. Instead of calling it 5 degrees C, we're going to call it some parameter A. Okay, so what we want to do now is we want to take the Laplace transform of this whole differential equation. So we're going to take the Laplace transform of that whole thing right there. When we take the Laplace transform of the left-hand side, what we get is S times capital Y of S minus T hat of 0. That would be your Laplace transform of your time derivative. Noting, of course, that we have defined Y of S as the Laplace transform of T hat. As I mentioned before, because we're working with deviation variables, and we initially start at a steady state, then our initial condition for T hat is 0. So that's the Laplace transform of the left-hand side of the equation. The right-hand side of the equation, you Laplace transform and the constant 1 over tau comes outside of the Laplace transform because it's a linear transform, that also means that it distributes over the two terms inside the parentheses. The Kp also comes outside of the Laplace transform, and so the next thing that we get is the Laplace transform of t1 hat. But the Laplace transform of t1 hat, since t1 hat at time t greater than 0 is just equal to this constant a, that Laplace transform is a over s, as you can see here. The second term inside the parentheses is the Laplace transform of t hat, which we've already covered is capital Y of s. So what we want to do is we want to solve this now algebraic equation for y of s. And what we get is y of s is equal to process gain times the magnitude of our step change, a, divided by tau, all of that divided by s times s plus 1 over tau. So all I did is I've taken this algebraic equation with one unknown, y, and I've solved it for that unknown. Now that we have y of s in this form, we want to be able to convert it back into the time domain. We want to get it back to use this solution for y of s to give us what is t hat as a function of t. So to do that, we have to get it into a form that appears using the common functions in the Laplace transform table. To skip ahead just a little bit, these are the two common forms that we want to find. We want to find a 1 over s and a 1 over quantity s plus a. But this right-hand side is not in either of those forms, so we want to convert it into a sum of terms that contain those two forms, and we can do that by partial fraction expansion. Now you probably saw partial fraction expansion before when you took calculus, I think 1 or 2, and you were trying to solve certain integrals. You were taught partial fraction expansion. In any case, what partial fraction expansion does is it makes it so y of s, which previously was equal to kp, I mean it's still equal to this, but we have expressed it as kp times a over tau, all divided by s times quantity s plus 1 over tau. That is also equal to, or it can be put in the form of, some constant c naught, c0 over s, plus some other constant c1 over s, let me back up. That's c1 and c2. c1 and c2. c1 over s plus some other constant c2 over s plus 1 over tau. So now it's on us to figure out what are the values of these two constants. Once we do, because we have these two terms that we can invert back into the time domain, when we do invert it back into the time domain, we will find out that t hat as a function of t is equal to c1 plus c2 e to the negative t over tau. So let's go ahead and figure out how to get c1 and c2. What we want to do is we want to multiply both versions of y of s by this denominator here. To do that, that gives us on the left-hand side just kp times a over tau. And on the right-hand side, part of this denominator that we're multiplying through cancels out with the denominator of the first term, and the other part cancels out with the denominator of the second term. And so just working out the algebra, you get on the left-hand side, the right-hand side, c1 times quantity s plus 1 over tau plus c2. Now this equation, it has to hold for every single value of s that we plug into it. So it also has to hold for particular values of s. So let's choose values of s that make our life easier. So if s were equal to 0, then this starred equation becomes kp a over tau equal to c1 times 1 over tau. Furthermore, if s equals to negative 1 over tau, then the starred equation becomes kp a over tau is equal to c2 times negative 1 over tau. So we can work through it, and therefore, this is an error here, sorry, in the notes. Therefore, C1 equals Kp times A, and C2 equals negative Kp times A. Because of that, then, capital Y of S is equal to Kp times A over S minus Kp times A over S plus 1 over tau. Now we have Y of S in a form that contains only terms that we can look up in the table, as I mentioned before, up here. So we can invert Y of S back to the time domain, and when we do this inversion, Y of S becomes t hat as a function of time. The inversion of Kp A over S just becomes Kp times A, and the inversion of negative Kp over A, negative Kp times A, over S plus 1 over tau, that becomes negative Kpa times e to the negative t times 1 over tau. No, sorry, e to the negative t over tau. My bad. Okay, and then you can simplify this further to get Kp times A times 1 minus e to the negative t over tau. And that is our final answer for t hat as a function of temperature. Now note, if I want to actually get t as a function of temperature, if I want to get t as a function of time, then t as a function of time is equal to t hat as a function of time plus t bar.